So I'm going to tell you about searches for neutrinos from WIMP dark matter. And this is a brief outline of my talk. I'll talk about the way that WIMPs can go to neutrinos, active neutrino detectors that have sensitivity to WIMPs, results from those active detectors, and then a brief survey of possible future detectors and their sensitivities. So last night I really enjoyed Jim Peebles' talk until the very end when he brazenly stole a quote that I was going to use from Yogi Berra at the end of my talk. So I therefore appeal to an equally renowned American philosopher to guide me through this presentation, which is the secret of life is honesty and fair dealing. If you can fake that, you've got it made. Okay, so with that in mind, I'll continue. So indirect detection, the indirect detection paradigm, as you all know, starts out with gravitational accumulation of dark matter, and there are lots of different places where this can occur, in the Earth, in the Sun, all the way up to galaxy clusters. And then those WIMPs either self-annihilate as Majorana particles or they decay, and that the annihilation is interesting because the interactions that give us the WIMP relic abundance allow self-annihilation in the current epoch. And this is proportional to rho squared. And there are two different channels, actually three, but the two main ones that we'll focus on in this talk are the hard and soft channels, which depend on either using W or tau typically for the hard channel or B's for the soft channel. And this sort of brackets the range of neutrino energies that we can see. And decay of neutralinos goes as the density, and of course the caveat that that violates R parity. Then the daughters of these WIMPs travel through space. And the nice thing about neutrinos is that they don't really care what's in between where the WIMPs are and where we are. So they penetrate dust and everything else. Whereas electrons and positrons don't make it very far. Photons can get absorbed. And protons will bend in magnetic fields, so you won't really know where they came from. So I'm going to focus in this talk, obviously, on neutrinos. And finally, what you have to do, and this is the hardest part pretty much for neutrinos, is detect them because they interact so weakly with matter. But there are three detectors that have done interesting things in searching for WIMPs producing neutrinos. That's Super K, Antares, and IceCube. So here are some candidate WIMP accumulators. The first is the Earth. And I list in parentheses after each possible accumulator which channel they can be detected in. And the Earth can only be detected, WIMPs in the Earth's core can only be detected through neutrinos. So the basic idea, which is the same for what happens in the Sun, and this is a nicer picture down here, so I'll focus on this one, is the neutralino bangs into a particle in the Sun or the Earth, and then eventually becomes gravitationally bound, ultimately ending up near the center where there are lots of other WIMPs, and there's an annihilation that takes place, and only neutrinos can get out. So that's what you look for, and the same is true in the Earth. The problem with the Earth is that it's rather not a very massive body, and so only slow and light WIMPs can be accessed by looking for neutrino signatures from WIMPs in the Earth, below about 50 GeV. It's also unlikely to be in capture annihilation equilibrium, so it's difficult to link whatever you do or don't detect, well, mainly what you don't detect, to physical quantities. And you focus in the Earth on spin-independent interactions. In the Sun, which is probably the most powerful channel, at least to date, for neutrinos, there's a wide range of WIMP masses that are accessible. WIMP evaporation keeps you from looking down below about 4 GeV in WIMP mass. And for WIMPs that have a mass greater than 1 TeV, the neutrinos that they produce will get absorbed in the Sun before they can get out. So that defines the upper limit of where you can look. The statement that the WIMPs in the Sun are in equilibrium is a statement that the annihilation rate is equal to half of the capture rate. And given that assumption, you can then extract the cross-section for WIMPs on nucleons. And in the Sun, you can access both spin-dependent and spin-independent interactions. So the other possible places to look are in the galactic center. Here, for most purposes, we assume WIMPs are collisionless. There was some discussion yesterday about whether it's cuspy or core-like. In any case, for WIMPs going to neutrinos, you extract the velocity averaged quantity the annihilation cross-section times the velocity of the WIMPs, or you can look for spectral lines. In the halo, we know the matter density pretty well, as was just demonstrated in the previous talk. You extract the same quantity. And for dwarfs and galaxy clusters, which, as was mentioned also in the previous talk, there's an attractive high mass to light ratio. Again, we extract the same quantity when looking for neutrinos. And there's also possible clumpiness, lots of mass. So it's a good place to also look for neutrinos. So as I've already mentioned, we consider the hard and soft channels as sort of extrema to bracket possible the neutrino energy spectrum. In the hard channel, we consider these decays, and the average neutrino energy from these decays is about 1/3 of the WIMP mass. In the soft channel, we focus on bottom daughters, and here the average energy is about 1/6 of the WIMP mass. And then you can also do line searches. And finally, what you do with the neutrinos that come out here, you focus mainly, for now anyway, on muon neutrino-induced muons in the detector. So the three experiments that have looked for WIMPs, I'll start out with the Super K detector, which has always seemed to get there first. This is one of the most successful neutrino astrophysical experiments, I think, that has ever been run. So it was designed originally for solar and atmospheric neutrinos at MeV to GeV energies. It has a fairly large volume, as you can see here. A fraction of it is their fiducial volume. They have 11,000 20-inch photomultiplier tubes. The sensitivity extends up to WIMP masses of about 100 GeV. There's a new idea, which I'll focus on a little bit later, by two of the authors of this new idea are in this room, for predicting, that predicts solar WIMP-induced flux of much lower energy neutrinos that Super K would be sensitive to. I think it's an interesting new idea. The other experiment that's been running is Antares. It's off the coast of France. It's a successful prototype undersea neutrino detector. Consists of 900 10-inch PMTs on the spacing that you see here, about 200 meters by 200 meters by about 350 meters in height. And the sensitivity for Antares is between 50 GeV and a TeV in WIMP mass. And finally, there's IceCube, which is the first operating kilometer scale detector for neutrinos. Consists of 5,000 10-inch PMTs. The little dots here represent PMTs on the spacing that's listed here. It was originally optimized for TeV to PeV neutrino energies. Then at pretty much the very last minute, in the last 2 years of the 7-year deployment of this experiment, we realized that we'd like to have sensitivity to lower energies. And so we built, and the specific reason for building this new infill array called Deep Core was to improve our sensitivity to lower mass WIMPs. And as I'll show you, it has achieved that goal and will continue to do so. So Deep Core is indicated by this greenish colored subdetector that's buried in the bottom center of IceCube. And it has denser module spacing in order to reach down to lower energies. So we're sensitive to WIMP masses from below about 50 GeV all the way up to energies above about 100 TeV. So now I'd like to talk about results. I'll start out with Super K. So Super K looks for solar WIMPs, and they use the following standard event topologies, which many of you have probably heard of before. The fully contained and partially contained events involve neutrinos that enter the detector and then interact. If the products don't escape, then it's fully contained. If they do, it's partially contained. And then they also look for upgoing muons, which stop in the detector or which go all the way through it. And they use two different analysis approaches to look for WIMPs. The first is what's called, by them, the Cowen half angle, and that's basically looking for high energy neutrinos coming from the direction of the sun. And the second is a spectral analysis where they look for a distortion in the atmospheric spectrum due to neutrinos coming from WIMP annihilations in the sun. And so what's shown here, it's difficult to read. That's the angular cut that they apply versus the WIMP mass. And what they try to do is choose a directional cut to keep 90% of their signal. And the angular cut here is at 10 degrees, 20 degrees, and so on. And so at for For the hard channel, labeled here tau tau, the partially contained and the up mu channels do the best, and likewise for the soft channel, partially contained and the up mu channels do the best as well. And over here is shown the fraction of the WIMP signal that has a specified one of these signatures from 10 GeV up to 100 GeV, and the end point here gives you an idea for how efficient the analysis was. So they are capable of detecting something like 80% of their signal. So it's a very high efficiency analysis in this energy range. So the procedure that they follow, which I'm going to list in some detail here because it's common to the other experiments, Antares and IceCube, is first to convert from the event limit into a flux limit using the knowledge that they have of the detector, so the live time and the detection efficiencies and so on. And then they convert from that flux limit into a cross-section limit. And to do that, they use code written by a theorist called Dark Suzy. They use a single annihilation channel, which is at a time, which is a more conservative approach, we feel. They assume equilibrium in the case of the sun. Ignore, in this case, SI scattering, spin-independent scattering, although that's not always true for other experiments, such as IceCube. And then there are standard assumptions that are used for the WIMP relic density and the velocity distribution. And they reach as low as almost 10 GeV, or I should say exactly 10 GeV in mass. So this is a result that was presented at Neutrino 2012 early this past summer. And other limits are shown here. I don't know if you can read these, but Picasso, CDMS, Xenon, Simple Coupe, and Dama Libra. So as I alluded to before, there are some possible future channels that Super K could look in. So the idea is that annihilating solar WIMPs will produce particle showers inside of the core of the sun. And those pions and muons will decay at rest. So the neutrinos that might have been initially produced will come out, and that's what's already been looked for, and that's mainly what's been looked for by these experiments. But there's also the possibility that the neutrinos from the pions and muons that decay at rest could be detected. Those would escape with characteristic energy spectra that are shown here. So this is the signal in blue here without energy resolution, and then in red with energy resolution. And the energy down here is up to the endpoint of about 50 MeV. So this is an energy range that is inaccessible to experiments like Antares and IceCube, but it's very accessible to an experiment like Super K. So the authors of this paper show that the sensitivity for Super K in this channel would allow it to possibly place a limit that's shown by this black line, and maybe even extend into this region where evaporation supposedly takes place, and could exclude part of Dama this way. So now I'd like to move on to Antares. Antares has searched for solar WIMPs, and they also say that they can search for the galactic center for WIMPs producing neutrinos from the galactic center. However, they don't have any results yet on the galactic center, so I'm just going to present their solar WIMP analysis quite briefly. So this is the mass of the WIMP here, and this is the effective area of the detector, which gives you a measure of how many events they should see. And in blue and in green and red are the hard, soft, and kind of hard channels that you would expect to see neutrinos coming from. And then there's also universal extra dimensions that they test as well. And then down in this plot is shown their sensitivity, which extends down to about 100 GeV in WIMP mass. So this shows their result. They placed a limit on the spin-dependent cross-section versus the WIMP mass shown here. So this is the logarithm of the cross-section in picobarns. And this is the mass of the WIMP in GeV. This is where the model, the CMSSM model, says you should look. Put in lots of different parameters into the model and mix them up, and you get all these different points here. And the red line, I believe, is the Antares limit, shown here for the hard channel, and then the dashed line is for the soft channel. And down here is shown their sensitivity for looking at the galactic center, I believe. I don't think I labeled this plot. So they have a sensitivity number yet, but not an actual limit. Okay, so now I'd like to move on to talk about IceCube and IceCube's results. So IceCube has looked for WIMPs from the core of the Earth, from the Sun, from the galactic center, from the galactic halo, from dwarf spheroidals, and also from galaxy clusters. We've been busy. So there's a dedicated online trigger and filter that has recently been put into place at the South Pole in order to enhance our sensitivity to Earth WIMPs. The reason for this is that those neutrinos that are produced will go directly up in our detector, and we'd like to lower our energy threshold as low as possible in order to be as sensitive to the lowest possible mass WIMPs. And in order to do that, we have to devise special ways to read out that data, because otherwise our normal triggering would just throw it away. So we've done that. One of the challenges of this analysis is that there's no off-source region that we can compare to. Atmospheric neutrinos are the main background. This plot over here on the right shows the Amanda analysis that was published in 2006. Amanda was the predecessor experiment of IceCube. And down here is shown what the predicted 10-year IceCube limit will be and how it will impinge on what's allowed, or what you get if you throw in a bunch of parameters and mix them up into, I think this is the CMSSM model here, and what part of that parameter space could be excluded. The actual Amanda limit excluded some piece of that, but not very much. And then there's another possibility that we can explore. Actually, it doesn't change our analysis at all, but only the way we interpret it. So what's shown here is that same 10-year limit. That's this dashed line is now superimposed on this plot. This is now the muon flux in per square kilometer per year as a function of the mass of the neutralino in GeV. And the two different plots show what happens if you assume that there's a dark disk, in which case the relative velocity between the Earth and the WIMPs in that dark disk would be lower, and so the cross-section would be higher, and you'd be able to exclude more of the parameter space. So the limit line stays the same place, but the parameter space moves up, so you exclude more of it. For solar WIMPs, what we do is we start out by creating a sample that's dominated by atmospheric neutrinos. And then to do that, we veto everything that looks like a downgoing muon, because that's a background that's about 1 million times more numerous than the atmospheric neutrinos. And then we take steps to maximize our efficiency for detecting horizontal events. And the reason we do that is because at the South Pole, the Sun, which is the source of these neutrinos, varies from being about 23 degrees above the horizon in the summer to being 23 degrees below the horizon in the winter. And we use the shape of the distribution of the space angle, labeled here with a psi, with respect to the Sun. And that distribution is shown here. So the background looks like this. The signal should look like that. And so this is one of the main selection criteria we use. We estimate the background by using time-scrambled data, which essentially moves the data in right ascension. And so if it was coming from the Sun, then it won't be, and we can use that as our estimate for the background. And there are a number of systematics that we need to take into account, such as our understanding of the properties of the ice, how well the modules can detect light, and the neutrino cross-sections. So what's shown here is a combined multi-year limit from Amanda, IceCube 22, which stands for IceCube when only 22 strings were installed, and IceCube 40. And just to show you what IceCube 40 looks like, IC40, this is a top view of the detector. Each circle here represents one of the strings that was deployed. And IC40 consisted of about half of the detector in this arrangement. IC22 was about half of that. And so here's the limit that IceCube provides in the hard channel, and here's the limit in the soft channel. And down here is what CDMS and Xenon would predict if you translate from the spin-independent to the spin-dependent cross-section. This is the spin-dependent cross-section limit here. So you see that these limits are in the same ballpark as the direct detection experiments. We also have some initial results from IC79. As you can guess, that's almost the full detector. The full detector is IC86 with 86 strings, but IC79 was a full cubic kilometer, and we have 1 year of data. That full IC79 detector included most of deep core. So that allows us to reach down to lower WIMP masses because we can now detect lower neutrino energies down to about 20 GeV. And we also improved the cosmic ray veto efficiency, which allows us to use not just the data that comes from below the horizon during the austral winter, but also the data from above the horizon during the austral summer. So that doubles our data set effectively. And so what's shown here is the sensitivity as a function of neutralino mass. The three different kinds of events that we look at that are shown here, they're either, if they're downgoing, so look at it here, downgoing that are produced inside the detector, so they're well contained, upgoing, and then number 2 there is events that don't go through deep core but are also upgoing. And so what we're looking for, again, with respect to the direction of the sun, is a big peak. This is a simulated 1 TeV WIMP, and this is what the data looks like. The scrambled data is the solid line, and the data points are the actual data that we see. And this funny shape here has to do with the fact that if you're looking towards the sun, and many of your events, background events, will be coming from above, and you're vetoing those events, you'll also lose a bunch of atmospheric neutrinos that are coming from directly above, and the angle between directly above and towards the sun is about 90 degrees. So that's where the depression comes from. Plus, we're not plotting cosine, but the angle itself. These are new limits. So I showed you before was the sensitivity. Now these are the new limits. So this is the IceCube limit in the hard channel, and the dashed line is in the soft channel. And I show here some preliminary super K results, which I didn't show you before, that extend the IceCube results, as you can see, down to substantially lower masses. Though IceCube has reached down to 20 GeV, we're not quite as good in that region yet as super K, but we'll get there. And this is the same plot, but spin independent. And you can see IceCube is almost down to where the direct detection experiments have reached. We've also looked at the galactic halo with IC22 and the galactic center with IC40. And these are the results. They're almost excluding the Fermi data using the positrons and partially excluding some of the PAMELA data. Of course, other experiments have done a better job at excluding that region. And we've also looked at dwarfs and galaxy clusters. And you can see the final limit here from IC59 using the Virgo cluster does a pretty good job and is fairly competitive with the other limits. And galactic halo and center analyses using IC79 and IC86. We have almost 2 years of data of IC86 plus a year of data of IC79 are underway. So we have quite a bit more data to look at, and we're actively doing that. So these limits are only going to improve. So now I'd like to quickly spend a few minutes and talk about possible future neutrino detectors. The first is Hyper-K, which is approximately a megaton and 100,000 phototubes. Its main focus is long baseline neutrino oscillations, but it can also do proton decay, atmospheric neutrinos, and astrophysical neutrinos. And it'll have sensitivity to neutrinos from WIMPs down to a WIMP mass of about a GeV. It's going to cost a lot of money. The time scale is roughly 2020. And this is a picture of what the detector might look like. And for lack of time, I won't go into detail here, except to say that their sensitivity for WIMPs is not as good as IceCube or KM3Net, which is another future detector I'll tell you about in a second, except when you go down to very low masses. And then they do better than anyone else can do. KM3Net is a cubic kilometer proposed experiment to be built in the Mediterranean. And there's a new, very recent rumor that they're also thinking about something called ORCA, which is a much smaller array to put in first. The original design was optimized for very high energy neutrinos, but it do have sensitivity to WIMPs, and that's shown here for the full KM3Net detector. And as you can see, they can exclude regions in green as a function of mass. They're also able to exclude the regions that are excluded, by Antares are shown in blue. So they can improve on that down to masses that are about 50 to 100 GeV. The other idea that they've recently floated is to use to something called ORCA, whose main goal would be neutrino hierarchy, and I'll talk about that in a second. But they'll also have sensitivity to WIMPs. No plots are available yet. But I think a rough guess for how sensitive ORCA will be to WIMPs will be shown by an experiment that's called PINGU, which is an extension that is also being discussed for IceCube for the same goal of neutrino hierarchy. We're a little bit further along than KM3net. The cost is not too high. One advantage they have is that they may already have the money in hand, which these days is an important factor to consider. And the time scale would be about 2018. And so finally, I want to mention the PINGU detector, which stands for Precision IceCube Next Generation Upgrade. The idea is to further increase the sensor density relative to deep core with 20 additional strings. And the top view of the detector geometry is shown here. The black symbols are IceCube strings that are separated by 125 meters horizontally. And then the red symbols are the existing deep core strings. And the blue symbols are what we propose to add to further infill the array, increase the density, and lower the energy threshold. The main idea is to get at the neutrino hierarchy using an energy threshold of a few GeV. But we can also get to very low mass WIMPs, around 10 GeV or so. The idea would be to use standard IceCube technology, so it would not be a technological challenge. We know how to drill holes. We can do it in our sleep, pretty much. We would include some new low-energy calibration devices. The collaboration consists of IceCube plus some other members from Europe and the US. The cost would be rather inexpensive compared to other experiments proposed to measure the neutrino hierarchy. Timescale would also be pretty quick, 2018. So just quickly, I'll show you the advantage of PINGU for a 9 GeV neutrino and split up into a 4 GeV cascade and track roughly. This is what you would see with deep core only. If you add PINGU, the number of photons that you collect, indicated by each of those colored dots, is up by at least a factor of 10. So we can reconstruct the events much, much better at low energies with the higher density. So the sensitivity of PINGU looks like this. So this is the very preliminary sensitivity to the hard channel for PINGU with 1 year of data, and we get down to roughly 10 GeV. And shown over here is what we might be able to do with the galactic center. And there's a point here at 5 GeV, which I wouldn't take terribly seriously. There hasn't been a lot of simulation done for this. But it's not totally ruled out that we could get down that low in WIMP mass. OK, so I'll conclude. Neutrinos are sensitive probes for detecting dark matter. The searches for the WIMP to neutrino signatures from distinct sources that I've just presented are, I think, self-complementary. And in addition, they're also complementary to searches using other astrophysical messengers. The current detectors continue to refine the analysis techniques, and they're getting more and more data. So things are only going to get better. There are clever new ideas, one of which I presented here for detection channels and for sources to look for, and these all spur new analyses. In fact, even though the 130 GeV line might turn out to be a canard, it has impelled us, on IceCube anyway, to look for line sources and to try to make an analysis that is most sensitive to line sources of neutrinos. And future detectors with lower energy thresholds will probe even lower WIMP masses, parameter space that has been made very interesting by direct detection experiments. Thank you.